Hello, welcome to the YouTube channel Decreation Resources. I am Dr. Deepthi and we are looking at different concepts from mathematics, and we are looking now at the concepts from matrices, which is a subfield in the broader field of linear algebra. So today let us look at the process of how to find out the symmetric and antisymmetric parts of a n by n square matrix. In order to do that, we need to revise some basic concepts. For example, the concept of transpose. Now, if you want to see it in detail, we have already done some videos, so you can have a look at it. Otherwise, here the gist of it is presented. Now, transpose of a matrix is basically its flipped version. So, if you consider a matrix M and if you consider an element which is in the ith row and jth column, in the transpose it becomes an element in the jth row and ith column. So basically the elements from rows and columns are switched. Now, had it been a rectangular matrix, the number of rows and columns would also have got switched, but here, since it's a square matrix anyway, both are equal. So now let us try to understand it with an example. Consider matrix A. It is a 3 by 3 matrix and the elements given are 1, 2, 3, 4, 5, 6, 7, 8, minus 1. Now in order to create its transpose, you have to switch the elements. So the elements from row 1 from the matrix A are going to be the elements from column 1 from the matrix A transpose. So 1, 2, 3, you can see them as column elements in case of first column element specifically in case of the transpose. And similarly, the second row from matrix A becomes second column for the transpose, third row for matrix A, namely the element 7, 8, minus 1, become column elements in the transpose, third column, 7, 8, minus 1. So this is the idea about transpose, where you switch the rows and columns. Now let us understand the second concept, which is the concept of symmetric matrices. So if the element from ith row and jth column is equal to the element from jth row and ith column, and if it is true for every element of a matrix, it is a symmetric matrix. We will understand this more using an example. So you can see here a matrix. The diagonal elements will remain as such because anyway it's going to be AII. So it will be equal to AII if you try to put it in the condition given above. But let us see the other non-diagonal elements. So the element in the second row and first column is 9. Now here it's a symmetric matrix because it is equal to the element in the second row, first row, second column. So in both the cases, it is 9. Similarly, minus 2. It's an element in the third row, first column. It is equal to the element in the first row, third column. So Aij is equal to Aji. You can see that it is true for even the rest of the elements. Of course, there are certain properties of these matrices. These are square matrices, and there are certain properties about its inverse. And if you add or subtract two symmetric matrices, they give you symmetric matrix again, etc., etc. So you can have a look at this in detail in some of the previous videos, and the properties are listed here. Similarly, you can understand the concept of skew symmetric matrix, which is also called as antisymmetric matrix. So here, especially we are looking at the real skew symmetric matrix where the elements are real numbers. So the element from ith row jth column is negative of the element from jth row ith column. So Aij is equal to minus Aji. This is the condition. So if you see here, 0, minus 2, 4 is the first row. Now, diagonal elements will have to be 0 if this condition is to be satisfied. So that is a given. Now, if you look at the element in the first row, second column, which is minus 2. So looking at the condition that Aij is equal to minus Aji, it has to be negative of the element in the second row first column. So as you can clearly see here, it is 2, which is negative of minus 2. Similarly, you will see that the element in the first row third column, which is 4, is negative of the element in the first column third row, which is minus 4. And same is true for 7 and minus 7. So this is an example of antisymmetric matrix, and it has its own properties. So as expected, it's a square matrix, its transpose is equal to negative of that matrix, diagonal elements are 0, and if you add, subtract, or multiply uh, a skew symmetric by symmetric matrices by a scalar, you are going to get a skew symmetric matrix. Now let us come to the important part which we wanted to discuss. So if it's a n by n square matrix A, and if its transpose is denoted as A transpose AT, then in order to find out its symmetric part and antisymmetric part, which we will denote as AS and AA respectively, we need to do a little bit of algebra. So if you add A to its transpose, that means A plus AT, and divide it by 2, you're going to get a symmetric part of A. Similarly, if you do the operation A minus A transpose and divide by 2, then you are going to get the antisymmetric part of it. Of course, if there's a straightforward proof for it, you can try to do it yourself, where you can just write A plus A and then add and subtract certain terms in simple algebra. Now let us look at the example. So here you have matrix A, again given as 1, 2, 3, 4, 5, 6, 7, 8, minus 1. Its transpose, as we had already seen, is given here. So now the symmetric part is going to be addition of these two matrices divided by 2. So the first element, 1 plus 1 is 2, divided by 2 is 1. So you get the first element. Similarly, consider first row, second column. This is 2 here, it's 4 here. 2 plus 4 is 6, divided by 2 is 3. So in the symmetric part, first row, second column, we get the element as 3. And similarly, you can do it for rest of the elements. So you can see that whatever you've obtained, it's a symmetric matrix. That means Aij is equal to Aji. So as expected, the first row second column element is equal to second row first column element, and so on and so forth. Now, in order to find out the antisymmetric part, you have to subtract A transpose from the matrix and divide by 2. So for example, if you consider the first element, 1 minus 1 is 0, divided by 2 of course is 0. And it doesn't come as a surprise. Because we are expecting an antisymmetric matrix or a skew symmetric matrix which has all the diagonal elements as 0. Consider the elements corresponding to first row second column. So it's 2 for A and 4 for A transpose. So 2 minus 4 is minus 2, divided by 2 is minus 1. So first row second column element in the antisymmetric part is minus 1. And similarly, you can try out the other elements. So basically, when you want to find out symmetric and antisymmetric parts, you have to add or subtract the transport and divide by 2, as the case might be. If it's a symmetric part, you have to add A plus A transpose divided by 2. And if it is antisymmetric, you have to subtract transpose from the original matrix and divide by 2. So it's a simple procedure, and you can of course try out the proof also. That is also very, very simple. Thank you.